All right, today we're going to tackle one of those classic physics problems that, just seems to trip everyone up. We're talking about the slippery chain problem. And here's the thing, this isn't just about plugging numbers into a formula. Nope, it's about learning how to think like a physicist when it feels like you're missing a crucial piece of information. So let's get right into it.
So picture this. You get a physics problem, it's all about friction. But they don't give you the coefficient of friction. How are you supposed to solve that? It sounds kind of impossible, right? Well, that's exactly the puzzle we're up against today. It might seem unsolvable at first, but I promise you the answer is literally hiding in plain sight, tucked away in the words of the problem itself.
Okay, let's get into this setup and really understand what we're dealing with. So, this comes from problem 1124 in Irodov. The scene is pretty simple. You've got a chain on a rough table, and a little piece of it is hanging over the edge. Now here's the key part. The problem says the chain starts to slide all by itself right when 1/3 of it is hanging down. Our mission? Figure out the total work done by friction from that moment until the entire chain slides off the table.
So what do we actually know? Let's break it down. We've got the mass of the chain, that's 0.8 kilograms, we have its total length, 1.5 meters, and we know that critical starting point. It starts to slide when 1/3 of it is hanging off the edge. And our goal, of course, is the total work done by friction. But look closely at what's not on this list. See it? There's no coefficient of friction, no K value. And that right there is the first mystery we have to solve.
All right, section 2, unlocking the hidden clue. This is where we need to put on our detective hats. Seriously, the #1 mistake I see students make right here is they panic. They see there's no K, and they think, I can't solve this. But trust me, the problem gives you everything you need. The clue just isn't a number. It's a sentence, a description of what's physically happening.
This right here, this single sentence, is the absolute key to the whole thing. The phrase starts sliding off the table all by itself. That's not just fluff. That is a very precise physics statement. It's telling you exactly what's happening with the forces in that one single moment. It's describing a system that's right on the brink, just on the verge of moving.
And what's that called in physics? Well, that's static equilibrium. It's this perfect, delicate state where the net force on the object is 0. The chain isn't actually moving yet, but it is just about to. Think of it like a tug of war where both teams are pulling with the exact same strength. Nothing's moving, but it's about to break. All the forces are perfectly, and I mean perfectly balanced.
So what are these balanced forces we're talking about? Well, it's a simple tug of war, really. On one side, you've got gravity. It's pulling down on that hanging part of the chain, the 1/3 of the total mass. That's our pulling force. And what's holding it back? That's the force of static friction, gripping the part of the chain still on the table, the other 2/3. That's our holding force. And here's the beautiful part. At that exact tipping point, right before it moves, these two forces are equal. The pull from gravity on the hanging part is perfectly matched by the maximum grip of friction on the table part. So we can just write an equation. The weight hanging down equals the friction holding it back. And just like that, we can solve for our so-called missing variable, K. See? It wasn't missing at all. It was just disguised in the problem's description.
And when you actually do the math, when you set the weight of 1/3 of the chain equal to the friction on the other 2/3, what do you get? You find that the coefficient of friction, K, is 0.5. A nice clean number. And remember, that number doesn't have any units. It's just a measure of how rough or grippy that table is. And there we have it. We found our hidden clue. First part done.
All right, next up, the force that fades. Okay, so we've got our K value. We're good to go, right? Home free? Not quite. This is where we run into the second big challenge in this problem, and it's a really common trap to fall into. We have to find the work done by friction, but, and this is a big but, the force of friction isn't going to stay the same. It actually changes the whole time. Just think about it for a second. What does the force of friction depend on? It depends on the normal force, right? Which depends on how much weight is pressing down on the table. So as this chain starts sliding off, what's happening to the amount of chain and all its weight that's still left on the table?
Right, it's decreasing. As more and more of the chain slides off, there's less and less of it left on the table. And less chain means less weight, which means less normal force, which ultimately means less friction. The frictional force is actually getting weaker and weaker as the chain slides. It's kind of like a car brake that's slowly losing its grip. So that means our simple old work equals force times distance formula? Yeah, that's not going to work here.
So, summing up the work, how in the world do you calculate the work done by a force that's not constant, a force that's changing every single instant? Well, for that, we need a special tool from our mathematical toolbox. We need something that can add up the work done over a bazillion tiny little steps. And that tool, my friends, is calculus, specifically integration. So yeah, work equals force times distance is out the window. Instead, we have to use an integral. Now, don't get spooked by the symbol. Just think of the integral sign as a big fancy S, and that S stands for sum. It's just a way for us to add up, or sum up, all the tiny little pieces of work. Each little piece is the force at that exact spot, f of x, multiplied by a teeny tiny step, dx. We just add them all up along the entire path.
And again, don't let the calculus freak you out. We can break this down into a super simple 3-step plan. Step 1, we need to write down a formula for our friction force. We need to describe how it changes based on x, which is just the length of chain left on the table. Step 2, we need to set our boundaries. Where does the sliding start and where does it end? Well, it starts when 2/3 of the chain is on the table, and it ends when there's 0 left. Easy enough. And step 3, we just do the integral and solve for the total work. That's it.
And once we actually follow that plan and perform the integration, once we've added up all those little bits of work from that fading friction force, we get our final answer, the total work performed by friction over the entire slide.
And the answer is negative 1.3 joules. Now, that negative sign is super important. It's not a mistake. Why is it negative? Think about it. What does friction do? It always fights against the motion, right? It's always trying to slow things down. That means it's removing energy from the chain. It's a dissipative force. So seeing that negative sign is actually a really good sign. It's a little sanity check that tells us we're on the right track.
Okay, section 4, the final answer and takeaways. So, we did it. We solved the problem. We found that hidden clue for K, we dealt with a tricky variable force, and we got our final answer. But listen, the real point here isn't just to get the number negative 1.3. The real goal is to understand the strategy we used, so you can take that with you and use it on other problems that look just as tough.
So let's add a few things to your physics toolkit. First, and this is the big one, you've got to read the problem statement like a detective. Look for those little phrases like starts to slide that are secretly telling you about the physics of the situation. Second, always ask yourself, are the forces I'm dealing with constant or are they changing? Because that one question completely changes your game plan. If a force is variable, you're almost certainly going to need to use calculus. And finally, break it down. Don't try to solve the whole thing at once. We found K first, then we worried about the work. Small, manageable pieces.
And hey, before we wrap up, here's a little something to think about. We just calculated the work done by friction, which is negative work. It's taking energy out of the system. But what about gravity? As the chain falls, gravity is doing positive work, right? It's adding energy and speeding it up. So my question to you is, if you use the work-energy theorem to account for both the energy lost to friction and the energy gained from gravity, could you calculate the final speed of the chain just as its last link leaves the table? That's the next step, and it's a perfect way to really test what we've talked about today. Think about it.